In this section, we're going to talk about electrical force. Electrical force. Electrical force is the kind of force that arises when two objects are rubbed together. For example, if you rub fur and rubber, the fur and the rubber will develop the property of attracting each other. And for example, let's say you comb your hair, you will see that that comb will develop the property of attracting pieces of paper. So this kind of force is a force that arises when two objects are rubbed together. This is a force that arises when two objects are rubbed together. Okay, so obviously some change must have taken place during the rubbing process that is leading to this kind of force. The change that took place during the rubbing process is called charge. The change that took place during the rubbing process is called charge. Okay, so it's very clear that something must have happened during the rubbing process leading to this kind of property of the two objects attracting each other, and that change is called charge. Now, let's say we have rubber and fur over here. When these two objects are rubbed together, they develop the property of attracting each other, rubber and fur. Okay, when they rub together, they will attract each other. Now, if you have another pair of rubber and fur, also they will attract each other. An experiment shows that these two rubbers repel each other. These two furs repel each other. So this tells us there are two kinds of charges. The kind of charge acquired by a rubber and the kind of charge acquired by fur. So when they're different, they attract each other. When they're the same, repel each other. So the conclusion is there are two kinds of charges. Okay, of charges, the one acquired by rubber and the one acquired by fur. And from this experiment, we see that when they are different, when they're opposite, they attract each other. When they're the same, they repel each other. So the conclusion is opposite charges attract and same charges repel. Mathematically, these two kinds of charges are identified as positive and negative. Okay, so mathematically these two kinds of charges are identified as positive and negative, negative. Okay, now the unit of measurement of charge is called coulomb. Unit of measurement of charge is called a coulomb, and we're going to use the abbreviation C. So the unit of measurement of a charge is called coulomb, and it's abbreviated by capital C. As you know, atoms are made of electrons and protons. The charge of an electron with this unit is negative 1.6 times 10 to the power of negative 19 coulomb, and the charge of proton and electron have the same charge, is 1.6 times 10 to the power of negative 19 coulomb. Okay, now let's see how we measure charges. Measuring charges. Charges are measured by a device called electroscope. Measured by a device called electroscope. Electroscope is simply, you got a jar like this, and then you have two gold leaves like this. Okay, so what happens is, when a certain charged object is brought in contact with the gold leaves over here, you see these two gold leaves occur the same charge. For example, let's say this is brought in contact with a negative charge, then these two leaves will occur negative charge and they repel each other. So these leaves are going to diverge if they're connected to a certain charge over here, right? And the deflection angle is proportional to the charge, which means by measuring the deflection angle, you can measure the charge. Okay, so an electroscope is simply a pair of gold leaves inside a jar like this, and when the jar or the gold leaves are brought in contact with a charged object, these two leaves acquire the same kind of charge and they push each other. Okay, and the deflection angle, because of the charge, is proportional to the amount of charge. So because of that, you can measure the amount of charge by measuring the deflection angle of the electroscope. All right, so nobody knows what charges are, but we're going to look at current understanding of charges. Let's look at current understanding of charges. Well, according to quantum mechanics, charges are actually a cloud, but the easier interpretation is what you call the Rutherford model. So we're going to look at the Rutherford model of the atom. Rutherford model of the atom. According to this model, the atom has a small nucleus that contains protons and neutrons. Okay, it has protons and neutrons in the center of the nucleus, and then you've got electrons moving around the nucleus like this. This is the Rutherford model of the atom. Okay, so you've got electrons moving around, and then you've got protons and neutrons inside. Neutrons don't have any charge, but protons have positive charge. Okay, so you got positive, so the nucleus of all is positively charged, and the electrons are negatively charged. Okay, so an atom is neutral, so normally it's going to have the same number of protons and the same number of electrons, because as a whole the atom is neutral, so the number of protons and number of neutrons are equal in an atom. Okay, so it's the Rutherford model. We have the central nucleus, which is very, very small, that contains protons and neutrons. Protons are positively charged, and then we have negatively charged electrons that are moving around the nucleus. So now, when one object is rubbed with another object, what happens is these electrons that are revolving around the nucleus will be transferred from one object to the other. So since electrons are negatively charged, the object that gained electrons becomes negatively charged, and the object that lost electrons becomes positively charged. So the current understanding is when two objects are rubbed together, objects are rubbed together, electrons will flow from one to the other. Electrons will flow from one to the other. Okay, now since electrons are negatively charged, okay, the object that gained electrons becomes negatively charged. The object that gained electrons becomes negatively charged, and the object that lost electrons electrons becomes positively charged. Positive charge. So this is the current understanding of charges. In atoms, you've got positive charges located at the center. So the charges that are moving around are the electrons, which are the negative charged electrons. So when two objects are rubbed together, the electrons that are moving around the nucleus will flow from one object to the other. And the object that gained electrons becomes negative charged because electrons are negative charged, because you'll have excess electrons in that object. And the object that lost electrons will be positively charged because it has the deficiency of electrons or negative charge, or it has more positive charges than negative charges. Now let's look at methods of charging. Methods of charging. Now there are two ways by which you can charge a neutral object. Okay, they're called conduction and induction. So let's look first at conduction. Okay, so this is a process by which a charged object is brought in contact with a neutral object. So in this process, a neutral object is brought into contact with a charged object. Okay, so let's say this is the neutral object over here, and let's say this is the charged object. Let's say this object is negative charged. Okay, so what's going to happen is these electrons over here, they're going to repel the electrons at this end. Okay, so the negative electrons will be pushed to this side over here, and so this end would be negative charged, and then this positively charged end will attract electrons. So the electrons will move from this object to this object because of that. Okay, so this object will acquire the same charge as this one. Okay, so this is a neutral object. What's going to happen? So electrons will be pushed to this side. This end will be positively charged, and then this end and this end will attract each other. So that attracts the electrons from this object to this object. So you see, this object will have excess electrons, and it's going to be negative charged. So in this process, the neutral object acquires the same kind of charge as the charging object. Okay, so the neutral object acquires the same kind of charge as the charging object. Okay, for example, in this case, this is the charging object. It was a negative charged object. When it's brought in contact with the neutral object, some of the electrons will flow this object, and this one also becomes negative charge. Okay, so the neutral object acquires the same kind of charge as the charging object. And the second kind of method is called induction. In this case, the neutral object is not brought in contact with a charged object. The neutral object is brought closer to a charged object without touching it. So in this case, the neutral object is brought near a charged object. So that without touching it. Okay, object without touching it. It's important. Without touching it. Okay, so let's say this is the neutral object over here. This is the neutral object, and then we have the charged object. Let's say this is the negative charged object. Okay, it has excess electrons. So what's going to happen is, as we've seen before, these electrons will repel the electrons on this end. So the electrons will go over here, and we'll have a net positive charge over here. Okay, after that, this end over here is connected to ground, is grounded. Okay, so the electrons would move from this object to the ground because the ground has low potential. All right, so what happens is this object will end up with a net positive charge because these electrons will go to the ground. Okay, so and then because of that we'll have a net positive charge at this object. So what happens, you see, this charging object is negative, but this will end up being a positive charge. All right, so in this kind of charging process, the neutral object ends up with a charge opposite to that of the charging object. That's the difference between conduction and induction. Okay, so the conclusion is the neutral object acquires a charge that is opposite to the charging object, okay? So this is the basic difference between conduction and induction. In conduction, the neutral object ends up with the same kind of charge as the charging object, but in the case of induction, the neutral object ends up with a positive charge to that of the charging object. Okay, so in conduction they're brought in contact, but in the case of induction they're just brought nearer, and then the neutral object is grounded and ends up with opposite charge to that of the charging object. Okay, and now let's look at insulators and conductors. Okay, so let's look at conductors first. Conductors, these are substances with free electrons, with electrons are free to move. Okay, these are substances with free electrons. Okay, electrons that are free to move around. Okay, because they have some properties. They are good conductors of electricity and heat. Okay, and they're ductile, they can be bent without breaking, and they're also usually very shiny. So usually metals. Okay, metals. All right, so conductors are substances with free electrons, and that gives them special properties such as being good conductors of electricity and heat, ductile and shiny. Okay, on the other hand, insulators, these are substances that do not have free electrons. These are substances that do not have free electrons. These free electrons are what you call valence electrons in chemistry. Okay, so because of that, they have the following properties. They are not good conductors of electricity and heat. They are not good conductors of electricity and heat. Okay, and they're dull, they're not shiny like metals, and they're brittle. They can be broken easily. I mean, it's not easy to change their shape, they're brittle. So these are some of the properties of insulators. Examples, you can say wood, rubber, glass, and so on. Okay, so far we've been talking about the qualitative aspect of electrical force. Now we're going to talk about the quantitative aspect of the force between charges. The law that governs the force between charges is called Coulomb's law. So we're going to look at Coulomb's law. This is the law that governs the electrical force between two charges. Okay, so let's say we have a charge over here and another charge over here. Maybe let's call this Q1, let's call this Q2, and then we have, this is a distance separating them. Okay, let's call R. This law says the force between two charges is proportional to the product of the charges. Actually, I should say to the absolute value of the product of the absolute value of the charges, and inversely proportional to the square of the distance separating them. Okay, let me write that in words first. It says that the force, this law states that the force between two charges is proportional to the charges and inversely proportional to the square of the distance separating them, Okay, so that means is if you double the distance, the force will change by a factor of 1 force. Okay, so let's write this mathematically. Let's say the force between these two charges is denoted by F. Okay, we're saying this is proportional to the charges, let's say absolute value of the charges, and inversely proportional to the square of the distance. Okay, so that means the force divided by this is a constant, so we can change this proportionality to equality by introducing a constant of proportionality. That constant proportionality is denoted by K. So going from equality to proportionality, we have the following: the force equals K, the product of the charges, and then divide by the square of the distance separating them. Okay, K is called Coulomb's constant. This is called Coulomb's constant, and its value is 9 times 10 to the power of 9. So the value of K is 9 times 10 to the power of 9 Newton meter squared divided by Coulomb squared. Okay, so this is a formula for the electric force between two charges. The force equals this universal constant K, and then you've got the product of the charges separated by the square of the distance separating them. Okay, so that's how you calculate the electric force between two charges. Okay, these charges are in coulombs and this distance is in meters, and of course you remember the unit of force is the newtons, and this is the value of this constant. All right, so that gives you how big the force is, but force is a vector, so we have to talk also about direction. So let's look about how we obtain the direction. Remember, there are two possibilities. If the charges have the same charge, they will repel each other, and if the charges are opposite, they attract each other. So that's how we tell the direction of the force. So if you're looking for what Q1 is doing to Q2, okay, if both of them have the same charges, either they're positive or negative, it's going to push it. Okay, so the force would be repulsion if these two charges are the same. Okay, so the direction of the force exerted by this one on this one will be this way. On the other hand, the force exerted by this one on this one will also be this way. You see, they're going to push each other, right? So if I ask you for the force exerted by this one on this one, it's going to be this way. If I ask you for the force exerted by this one on this one, it's going to be this way. On the other hand, if they are opposite, let's say it's positive and it's negative and this negative is positive, they're going to attract each other. Okay, so in that case, they will attract each other. This object will attract it this way, and this object will attract this way. Okay, so if I ask you, let's say they have opposite charges. If I ask you for the force exerted by this one and this one, it's going to be attraction. If I ask you for the force exerted by this one and this one, it's going to be attraction this way. So there are two possibilities for the attraction. If the signs are the same, it's repulsion, they push each other. If both charges have opposite signs, they attract each other. The force is attraction. Okay, and the direction of the force is along the line joining the centers of the two charges. Okay, so let's look at direction. Okay, first of all, the direction is along the line joining their centers. Okay, and if they have the same charges, they push each other. If they have opposite charges, they attract each other. So if they have the same charge, that's the same sign, the same charge, they repel. They repel and push each other. Okay, and if they have opposite charges, if they have opposite charges, okay, they attract and pull each other okay, so that's how we know the direction. If they have the same sign, they push each other. If they have opposite sign, they attract each other. Okay, so let's look at an example now. Example, suppose we have the following situation. Let's say this is a positive charge, and let's say Q1 is maybe 2 microcoulomb, and then we have another charge over here. Let's say it's Q2. Let's say it is negative 3 microcoulomb, and let's say this distance over here is, let's say, 1 millimeter. Okay, so first let's say calculate the magnitude and direction of the force exerted by Q1 on Q2. Okay, so now I'm looking what this charge is doing to this one. Okay, when I say the force exerted by Q1 and Q2, I'm looking what this charge is doing to this one. Okay, first let's do the magnitude. Okay, the magnitude is, this is a force on 2 by 1, okay, is K, absolute value of Q1, absolute value of Q2. Remember, magnitude is always positive, so make sure you put the charges in absolute values. Okay, so putting the numbers, and R is 1 millimeter, so you've got R is 10 to the power of negative 3 meters. Okay, so we get K is 9 times 10 to the power of 9. Okay, in Q1, micro means 2 times 10 to the power of negative 6. All right, and Q2, remember, it's absolute value, so we don't include the negative, so it'll just be 3 times 10 to the power of negative 6, okay, divided by the distance squared, which is 1 millimeter, or 10 to the power negative 3 squared. Okay, so first let's look at the numbers. 9 times 2 is 18, 80 times 3 is 54. Okay, so we've got 54 times, let's look at the power of 10. We've got negative 6 is negative 12. Negative 12 plus 9 is negative 3. But at the bottom we have negative 6. Okay, so it's 10 to the power of negative 3 plus 6. Okay, that's 10 to the power of 3. So from the powers we get 10 to the power of 3 newtons, and the unit of force is newtons. Okay, so this is the force exerted by this charge on this one. How about the direction? Let's look at the direction now. First we look at the signs. Okay, this is positive, this is negative, so they're going to attract each other. Okay, so we're looking what this charge is doing to this charge. It's going to attract it, which means the direction of the force is this way, which is west. Okay, so direction is west, or in the direction of the negative x-axis. Okay, now we're going to ask the same thing for Q2. Calculate the magnitude and direction exerted by Q2 on Q1. Okay, now you see these two forces are action-reaction forces. You see, remember Newton's third law? For every action there's an equal and opposite reaction. So if this is exerting this force on this one, from Newton's third law, this will also exert force the same amount but in the opposite direction. Okay, so we can say F12 is equal to F21. They're action-reaction forces, so if you use the formula, it'll be the same. There is a difference. So it'll be this one, 54 times 10 to the power of 3. And its direction will be opposite to this one. Okay? We're looking what this is doing to this one. The signs are opposite, so it's going to attract it, so it's going to pull it towards east. Okay? So the direction is east. Now, how about if there are a number of charges in the vicinity of a charge? So we're going to look at what they call the superposition principle. Superposition principle. Okay, let's say we're trying to calculate the force acting on this one, and there are a number of charges around it. Let's say this is Q1, Q2, Q3. Okay, so how do you calculate the net force acting on this one? All you do is you calculate the force by each, by this one, by this one, by this one. You add them together. Okay, but these are vectors, so they're going to be added like vectors. Okay, so if there are a number of charges in the vicinity of a charge, the net force acting on the charge, is the vector sum. These are vectors, so that's important. The vector sum of all of the forces exerted by the charges. Okay, so if the charges are F1, Q1, Q2, and so on, so we'd say the net force is simply the sum of the forces. You get the force exerted by charge 1, and then you add the force exerted by charge 2, you add the force exerted by charge 3, and so on. Okay, so there are a number of charges in the vicinity of a charge. All you do is you calculate the force by each charge, and then you add them vectorially. Okay, so in this section we're going to have to add vectors. We have discussed addition of vectors last time, but let me remind you how to add vectors before we look at some examples. Okay, so let's say review of vector addition. Vector addition. Okay, so what is the sum of two vectors? For example, you take the displacement per particle. Let's say you displace it first this way to the east, and then displace it to the north. What we call the sum of these two vectors is the single vector that does the same thing, the vector that takes it from here to directly. Okay, so that's what you call A plus B. Alright, so to add graphically, all you do is you connect the two vectors tilted like this, then the vector connecting the tail of the first vector to the head of the last vector is what you call the sum of the two vectors, also sometimes called resultant. Okay, now let's see how we can do this mathematically using the concept of components. I'm sure you remember what components mean, but let me revise it very shortly. Components. So if you have any vector like this, okay, let's say its magnitude is A, its direction is theta over here, this projection is on the x-axis, and the projection of the y-axis are what you call the x and y components. Okay, so we call this the x component of the vector, and we call this one the y component of the vector. And if this angle is theta, using the definition of cosine, you can easily find out ax equals a times cosine of theta, and ay equals a times the sine of theta, provided you use the default angle. The default angle is angle measured with respect to this line. Okay, so let's say you're given this vector and you're given this angle, but if you want to use these formulas, you have to use this angle over here, angle measured from here. Okay, this angle is positive when measured in a counterclockwise direction and negative when measured in a clockwise direction. Okay, so if you measure the angle from here, this formula will always give you the right sign of the vector, because these components could be positive or negative. You see, the x component is positive to the right, negative to the left. The y component is positive up, positive down. Okay, but if you use this angle measured from here in this formula, you'll always get the right sign. So that is how we calculate the component of a vector. Okay, now let's see how we can add them analytically or algebraically. Okay, suppose, let's say we have the following two vectors. Let's say this is the first vector, this is the second vector. Let's say this is A, this is B. Okay, and then from the graphical method we know that this is the sum of the two vectors. Let's call it R. R equals A plus B. Okay, now let's look at the components. You see, this one would be AX, this one would be AY. If you look at this vector over here, you see this would be the y component of B, and this would be the x component of X. Now if you look at the sum, which is R, you see, this is R. You see that from here to here is going to be Rx, and from here to here is going to be Ry. Now you can see very easily Rx is the sum of these two, Ax and Bx. Okay, so we have Rx equals Ax plus Bx, and Ry, you see, is from here to here is simply Iy plus By. So we've got Ry equals Ay plus By. Okay, so the general rule is if R equals A plus B, then Rx is the sum of the x's and Ry is the sum of the y's. Okay, now look, we're here now. this is r, this is ax plus bx, it's x component, and this is ay plus by. Okay, so from Pythagorean theorem, we're trying to obtain these two, magnitude and direction of the sum vector. Okay, we can obtain r from Pythagorean theorem, which is square root of ax plus bx squared, and then we got ay plus by squared. Okay, and then for the direction we can use tangent, so theta equals tan inverse of the opposite side, which is ay plus by, divided by ax plus bx. Now remember, if this is negative, you have to add 180 degrees. Okay, so let me say over here plus 180 degree if ax plus bx is less than 0. Okay, you look only at this one over here. Well, the reason is, take these two situations. Let's say this is force 3, and then with the opposite vector, force 3. Okay, if you want to calculate this angle, this is negative to negative 4. The calculator will give you tan inverse of 3 over 4. Okay, this angle will be tan inverse of 3 over 4. But if you do the same thing for the calculator, okay, we're looking for this angle, the calculator will give you also the same thing. This will be tan inverse of negative 3 over negative 4, which is the same thing. So this will give you 37 degrees, this will give you 37 degrees. Okay, so the calculator doesn't distinguish between these two because negative is positive. So if you're on this side, that is, if this is negative, what it is, the calculator will give you this angle, you have to add this 180 yourself. Okay, so remember, if this is a negative number, the calculator does not give you the right answer. You have to add 180 degrees. Okay, so that is how you add vectors. First, you find the components of the two vectors, okay, and then use these formulas to calculate the magnitude and the direction of the sum vector. Okay, now let's look at some examples. First we're going to look at a one-dimensional problem. Okay, suppose let's say we have Q1 over here, maybe it is 2 microcoulomb. Let's say we have another charge over here, let's say it's Q2, maybe negative 1 microcoulomb. Let's say this distance over here is 10 meters. Okay, and then we have, let's say, another charge over here, Q3. Let's say this is 3 micrometers, and let's say this distance over here is, this is millimeters, and let's say this is 20 millimeters. Okay, so the question is, calculate the net force exerted on Q3 by Q1 and Q2. Okay, so we want to know what's happening to this one. So this charge is being acted upon by this charge and by this charge. We have two forces, force on 3 by 1 and force on 3 by 2. Okay, so you can say the net force acting on 3 is the force exerted on 3 by 1 plus the force exerted on 3 by 2. Okay, so we have two forces, and we have to calculate these two forces and add them together. Okay, so let's look at F31 first, the force exerted on 3 by 1. Okay, first we're going to calculate the magnitude. The magnitude is this one, F31 equals K, absolute value of Q1, absolute value of Q3, divided by the distance between 1 and 3 squared. Okay, so what are the charges? where we're given Q1 is 2 times 10 to the power of negative 6 meters. Remember, micro means 10 to the power of negative 6. And then Q3 is 3 times 10 to the power of negative 6. And then the distance between 1 and 3, you see you've got 10 millimeter plus 20 millimeters, 30 millimeter. So this one is 30 times 10 to the power of negative 3, or 3 times 10 to the power of negative 2 meters. Okay? So the magnitude will be as follows. The magnitude would be F31 equals 9 times 10 to the power of 9, and then Q1 is 2 times 10 to the power of negative 6, and then we have Q3, 3 times 10 to the power of negative 6, divided by the distance squared, which is 3 times 10 to the power of negative 2 squared. Okay, let's look at the number. The square of 3 is 9, so that will kill this 9 over here. So we just have 2 times 3. Okay, so the numerical value is 6. Now let's look at the powers. This is negative 12 plus 9 is negative 3. So we have negative 10 to the power of negative 2 at the top. Over here we have 10 to the power of negative 4. Okay, so when it goes up it becomes plus, so it's just times 10 to the power of 1 newtons, or 60 newtons. Okay, now let's look at the direction. The direction is, this is positive, this is positive. So this charge is going to push this charge, so the direction is going to be this way. Okay, so the direction is east. Okay, so in this case we don't have vertical forces, we have only x components. So this will just, we can say the x component is 60 because this is the right. Okay, if it was to the left, it'll be negative. We have only x components in this case. All right, so we're going to do the same thing for F32, force on 3 by 2. Okay, so let's do F32. Okay, first we're going to look at the magnitude. So the magnitude of the force exerted on 3 by 2 equals K Q2 Q3 divided by the distance between 2 and 3 squared. Okay, so Q2 is negative 1 times 10 to the power of negative 6. Q2 is negative 1 times 10 to the power of negative 6 coulomb. The distance, you see, the distance between charge 2 and 3 is this one, which is 2 times 10 to the power of negative 2 meters. So the distance is 2 times 10 to the power of negative 2 meters. And of course, Q3 is 3 micro coulomb. Okay, so Q3 is 3 times 10 to the power of negative 6 coulomb. Okay, so from these numbers we can calculate F32. So you've got F32, that is force exerted on 3 by 2, equals the constant K, 9 times 10 to the power of 9, and then the charge Q2, remember, is absolute value, so we're not going to include the negative, negative 6, and then Q3 is 3 times 10 to the power of negative 6, and the distance is 3, this is 2, 3 times 10 to the power of negative 2 squared. Oh, is the distance 3 between, no, it's just 2, I'm sorry. The distance between 2 and 3 is just 2. Oh, this is a charge, I'm sorry, this is a charge, this is a charge, I'm right, this is 2 over here. Okay. All right, so let's look at the numbers. We've got 9 times 1 times 3, 27. At the bottom we have 2 squared, which is 4. Now let's look at the powers of 10. You've got negative 6, negative 12, negative 12 plus 9, negative 3, but we have negative for the bottom. When it goes up it becomes plus 4, so we just get times 10 newtons. Okay? Now let's look at the direction. Look, we're looking at what this is doing to this one. So this is negative, this is positive. So it's going to attract it. Okay, so the direction is west. All right, so the direction for this force, the vector, is west. Or you can just simply say the component, the x component, I have one x component over here, is negative because it's directed towards west, 27/4 times 10. Okay, so that's it. We have the two x's. So the net x now, we have only x's, so we can say the x of the net is the x of the force exerted by 1 plus the x of the force exerted by 2. Okay, so we have these numbers. This one is 60 to the right, positive, and this one is negative. Okay, minus 27/4 times 10. Okay, so which one is bigger? We have this is by 5 by 2, so you got 13.5. This divided by this would be 13.5. 13.5 by 5 would be about 67.5, I think. 67.5. Okay, so this is approximately negative 7.5 newtons. What does the negative means? That is, the magnitude is 7.2, but the direction is west. So we have F net equals 7.5, and its direction is west because this turns out to be negative. Okay, that's it. Okay, next we're going to look at a two-dimensional problem. Two-dimensional problem. So let's say we have the following situation. Let's say we have a charge over here. Let's call it Q3. Let's say we have a charge over here. Let's call it Q2. Let's say we have another charge over here. Let's say we call this one Q3. Okay, so let's say this is -1 times 10 to the power of maybe -9 micro. This one, let's say, is 2 times 10 to the power of -9. I mean nano coulomb. And then let's say this one is 3 millimeters. This one is 4 millimeters. This one is 4 millimeters. Okay, and this charge, let's say it is 3 times 10 to the power of -9 coulomb. Okay, so the question is, determine the net force acting on Q3 by charges Q1 and Q2. Okay, so we have two forces. The force exerted by let's say this is 1, this 2. The force exerted by 1 on 3, and the force exerted by 2 on 3. Okay, so you've got the net force on 3 equals the force exerted by on 3 by 1 plus the force exerted on 3 by 2. Okay, that's what we have to find. First we have to obtain the force exerted by 3 on 1 and the force exerted by 2 on 3. Okay, so let's look first at the force exerted on 3 by 1. Okay, first we're going to magnitude. Magnitude is K, absolute value of Q1, absolute value of Q3, divided by R13 squared. Okay, let's look at the numbers now. This is Q1. Okay, so you've got Q1 is 2 times 10 to the power of 9 coulomb. Q3 is 3 times 10 to the power of negative 9 coulomb. Now the distance, this is the distance. Okay, the distance to charge is this one. But we know this is 3, we know this is 4, so we can use Pythagorean theorem to calculate it. Okay, so this distance R13 is the square root of 3 squared plus 4 squared millimeter, which is 5 millimeter. Okay, that is 5 times 10 to the power of negative 3 meters. Okay, so we have the numbers. So now we can just put the numbers. Okay, so we've got 9 times 10 to the power of 9. Q1, 2 times 10 to the power of negative 9. Q3, 3 times 10 to the power of negative 9. And then the distance, 5 times 10 to the power of negative 3 squared. Okay, that's the magnitude. Now let's look at the numbers. We've got 9 times 2, 18, 8 times 3, 54. And then we've got 5 squared at the bottom. So the number is, we're looking at F31. We've got 54 at the bottom, at the top, 25 at the bottom. All right. Now let's look at the powers. 9 plus negative 9 is 0. So we have negative 9. And then we've got negative 6 over here, so it's going to be negative 3. So this is times 10 to the power of negative 3 newtons. So that's the magnitude. All right. Now let's look at the direction. Okay. So this is positive. This positive is going to push it. So you see the force exerted by 1 on 3 is in this direction. Okay, so its default angle is this one. So how do you calculate this one? You see these two angles are equal because they're vertically opposite angles if you remember geometry. So to calculate this one, all I have to do is calculate this one. And this one, you see I can use this right triangle over here, is tan inverse of 4 over 3. Okay, I'm looking at this right angle triangle over here. The opposite side is 4, the adjacent side is 3. I get tan inverse of 4 over 3. So the direction, that is theta 3, 1, is tan inverse of 4 over 3, which is 53 degrees. Okay, so we have the magnitude and the direction for F1. Now what we need is the components. All right, so let's calculate F31x and F31y. Okay, so this will be F31 times cosine of theta 3, 1. Okay, so that is F31 is 54 over 25 times 10 to the power negative 3 times the cosine of 53 degrees. The cosine of 53 degrees is approximately 0.6, okay, or 3 over 5. So we have, this is 54 over 25 times 10 to the power negative 3, and then times 0.6 or 3 over 5. Okay, so you've got 150, 170 over 125 times 10 to the power of negative 3 newtons. Okay, and then we'll calculate F31y. That's going to be F31 times the sine of theta 3 1. Okay, the magnitude is 54 over 25 times 10 to the power negative 3 times the sine of 53. That's about 0.8 or 4 or 5. Okay, so you got 54 over 25 times 10 to the power negative 3 and times 4 over 5. Okay, so this is 216 over 125 times 10 to the power negative 3 newtons. Okay, so we have the x component and the y component. All right, that's what we need. Now we're going to do the same thing to the second force, the force exerted on 3 by 2. So next we're going to look at this one, the force on 3 by 2. Okay, so first we're going to look at the magnitude. 3 2 would be K Q2 Q3 divided by R23 squared. Okay, let's look at the numbers. Q2 is right over here, is negative 1 times 10 to the power of negative 9. So Q2 is negative 1 times 10 to the power of negative 9 coulomb. And Q3 is this force over here, 3 times 10 to the power of negative 9 coulomb. 3 times 10 to the power of negative 9 coulomb. And R23 is the distance between charges 2 and 3. Okay, so R23 is this one. This distance is R23. Okay, so we have the right angle triangle over here. This is 3, this is 4, so this is from Pythagorean theorem, the square root of 3 squared and 4 squared. So R23 is the square root of 3 squared plus 4 squared millimeter, which is 5 millimeter, or 5 times 10 to the power of negative 3 meters. Okay, so we have the numbers. Now let's calculate. So F3 is K is 9 times 10 to the power of 9. Okay, Q2, remember it's outside value, so we don't include the negative. So we've got 1 times 10 to the power of negative 9. And Q3 is 3 times 10 to the power of negative 9, divided by the distance, which is 5 times 10 to the power of negative 3 cubed. Okay, so let's look at the number first. 9 times 1 times 3 is 27. And 5, no, this is squared, I'm sorry. 5 squared is 25. Okay, let's look at the powers. 9 plus negative 9 is 0. You got negative 9, but you got 6 plus 6 from this. That's negative 3. Negative 3. Okay, that is the magnitude of the force, Newton. That is F32, the magnitude. Now let's look at the direction. Okay, the direction of this force. Okay, look, this is positive, this is negative. So looking at what this charge is doing to this charge, since they have opposite charges, it's going to attract it. So it's going to be this way. Okay, so the direction of the force will be this way. This will be the force on 3 by 2. Okay, so the default angle for this force is this one. This one over here. So how do you calculate it? You see, we can calculate this angle because from this right angle triangle, we know this is 3, this is 4, we can calculate. So if you call this alpha, the angle we need is 180 minus this angle. Okay, so we can say theta 32 is 180 degrees minus alpha, but alpha is tan inverse of 4 over 3, right? So you've got 180 degrees minus tan inverse of 4 over 3, and that is 53 degrees. This is 53 degrees. 180 degrees minus 53 degrees is 127 degrees. Okay, so that's the direction. Now we have the magnitude, we have the direction, we can do the components. Okay, so you've got f32x equals f32 times the cosine of theta 32. Okay, so this one is f32 is 27 over 25 times 10 to the power negative 3, and cosine theta 32, this angle is 53, so it's going to be times 0.6, all right, times 3 over 5 negative. You see, it's going this way, so its component is this way, so it's going to be a negative number over here. All right, the cosine will be negative in this case. All right, so this would be, this is 3 times 2, 60, 81, negative 81 over 125 times 10 to the power negative 3 Newton. Okay. Okay, now we're going to the y component, f32y, f32y, this will be the magnitude f32 times the sine of theta 32. Okay, so the magnitude you saw over here, it is 27 over 25, 27 over 25 times 10 to the power negative 3, and the sine of 53 degrees, okay, which is 4 over 5 or 0.8. So we've got 27 over 25 times 4 over 5 times 10 to the power of negative 3. Okay, this one is positive. So this is 80 plus 28 is 108 divided by 125 times 10 to the power of negative 3. Okay, so we have the y component, we have the x component for both of them, and we have also the same thing for f1. We have the y component, we have the x component. Now all we do is use the formula to calculate the magnitude and the direction. Okay, let's start with the magnitude. The magnitude f net on 3 equals square root of, you add the x's, okay, 31x plus f32x, you square it, and then the y, f31y plus f32y squared. Okay, so we just plug in the numbers. All right, so what is f31x? f31x, and this one over here, 170 over 125, 170 over 125 times 10 to the power of negative 3. How about f32x? f32x, this one over here, negative 81 over 125, negative 81 over 125 times 10 to the power negative 3 squared. We do the same thing for the y's. f31y is 216 over 125, 216 over 125 times 10 to the power negative 3, and then f32y is right over here, plus 108 over 125 times 10 to the power negative 3. Okay, we have to calculate this one, the squared. So as you can see, we can factor out this one, the square root of 125, and well, they're squared, so we've got 125, 1 over 125 times 10 to the power negative 3 can be factored out, okay? So you've got the square root of, you see this are all 125, these are all negative 3, so it can be factored out, okay? So we've got 170 minus 81 plus 216 plus 108 squared, okay? So whatever that number is going to be the magnitude of the net force. How about for the direction? For direction, we're going to say theta net equals tan inverse of f31y plus f32y divided by f31x plus f32x. Okay, so as you can see, this common factor is going cancel out, so these are basically the x and the y's we need. So you can say this is tan inverse of the y, which is 216 plus 108, and then the sum of the x's 170 minus 81. Okay, the reason we're carrying this is because we'll cancel out because it's over here, all right? Okay, that'll be the direction, and this angle is positive, so we don't have to add anything. We calculate the calculator, that's going to be our direction, that's going to be our magnitude.